The T92 Rotary Tribometer consists of an upper mounting plate to which is mounted motor connected to the spindle via belt drive, spindle with a torque limiting hub, torque reaction assembly, magnetic sensor for emergency stop circuit, crossbeam mounted on linear bearings, base plate with mounting position for load actuator. The machine frame contains the electrical power module containing the motor drive, heater control circuits, e-stop safety relay, control relays, fuses and MCBs. A signal box with load and friction zeroing potentiometers, load override safety switch, load cell and thermocouple amplifiers, and an instrument cabinet with an interface module for PC communications. Under the top cover is the belt drive between the motor and the test spindle. The test spindle is fitted with a torque limiting hub, as well as a speed sensor and a contact potential slip ring. Fitting the low load actuator requires two people. Firstly, remove the transport clamps from above the crossbeam. Secondly, raise the crossbeam and clamp into place. Taking care not to hit the torque transducer. Fit the load actuator in place using the correct adapter tube in the base plate of the machine, with the air fitting and the load cell cable to the rear of the machine. Connect the air pipe from the machine base into the air fitting and connect the load cell cable, ensuring the two red dots and the connectors are aligned. Finally, lower the crossbeam into place, taking care to ensure the transducer is seated in the crossbeam. Allow the bellows to compress slightly, but do not put the full weight of the crossbeam. Finally, clamp both clamps into place to hold the crossbeam. The machine is supplied without the thrust bearing fitted, and this must be fitted before operating the machine. The bearing should be fitted to the bearing support on the crossbeam of the machine. It is important that the bearing is fitted the correct way round. The spigot should be a tight fit through the race, which is fitted to the top of the bearing, as demonstrated here. Fit the race with a loose fit at the bottom. Ensure that it is pressed down correctly. Then fit the cage and the upper race. Finally, fit the spigot in place through the bearing. The machine is fitted with a temperature failsafe module which will turn off the power to the machine if the temperature of the test assembly is higher than that of the alarm set. This temperature is measured using a separate thermocouple from the specimen temperature. When turning on the machine, after a short while, the current temperature being recorded by the thermocouple will be displayed. The red alarm reset light will be illuminated. Press in the button and the machine will turn on. If the overtemperature thermocouple is not connected, the display will show open and the alarm will not be able to be reset. When a thermocouple is plugged in, the display will eventually show the current temperature and the machine won't be able to be reset. To adjust the alarm level, press the left button until the display shows AL1. After a few seconds, the display will change to the alarm set point, in this case 70 degrees. Use the middle and right buttons to adjust the alarm level. Then press the left button until the display shows PROC. Wait for a few more seconds and the display will now show the current temperature. If the alarm level is set lower than the current temperature, the machine will not be able to be turned on. The machine will not be able to be powered on until the alarm level is set higher than the current temperature. Instrument box, press the blue reset button. The button will illuminate, showing that the machine is enabled. The blue button will only illuminate provided all of the e-stops are released and the machine guard is fitted. Pressing in any of the emergency stop buttons disables the machine. With the emergency stop buttons pressed in, the machine cannot be reset. To release the emergency stop, twist the head. Then press the blue button again to re-enable the machine. Likewise, removing the guard disables the machine. The machine cannot be re-enabled until the guard is refitted. The load override switch will be illuminated in normal operation, provided the air supply is on and at the correct pressure, and the machine is enabled, i.e. the blue light is illuminated. When the load override button is pressed in, the light will turn off after a short delay. The load will not be applied when the light is off. The load operation select switch allows the user to bypass the emergency stop circuit and apply a load without the machine enabled, i.e. the blue lights are on. The machine is fitted with a vibration sensor integrated with the emergency stop circuit. The sensitivity of the circuit can be set so that the machine will stop automatically in the event of the failure of the specimen. The sensitivity is adjusted using the potentiometer on the front of the power mod. The yellow vibration test light will illuminate when the sensor detects vibration. The e-stop is triggered if the sensor detects sustained vibration for approximately 2 seconds. This is indicated by the machine active light not being illuminated. The vibration cutout is reset using the vibration reset button. This is not illuminated. The machine can then be re-enabled in the usual way. The circuit may also be checked by holding in the vibration test button. The load operation select and the RMS to DC switch are mounted on the rear of the interface cabinet and may be accessed from the rear of the machine. Fitting the upper hub. First, remove the R-clip and withdraw the pin from the hub. Fit the hub over the shaft. The hub aligns with the lower set of holes in the shaft. Fit the pin through the hub and the R-clip to secure the pin. Fit the specimen holder using the correct supplied screws in the appropriate holes in the upper holder. In this case, the specimen is already fitted to the holder. Carefully pass the specimen bath into the position on the load beam. Ensure that the torque reaction arm is aligned with the torque transducer. Connect the heaters. Connect the over temperature thermocouple as appropriately marked. And connect the specimen thermocouple.
We are now ready to move from the machine to the PC. Double-clicking the COMPEND icon on the Windows screen launches the software at page 1, the primary user interface screen. A single screen or page contains up to 40 boxes, and there are a total of 6 pages. Pages 3 and 4 are available for controlling additional peripheral devices, if required, and for additional sensors and derived channels. Page 5 is used for calibration. Page 6 duplicates boxes from page 1 and is used to define the order of columns in data files. It may also contain machine status information that can be used for fault finding. The current page number is shown in the top right-hand corner. The page displayed may be changed with a right or left click of the mouse or by pressing the page up or down key on the keyboard. Clicking on the File menu and selecting Show Setup displays the current setup and calibration files. The software version number and the configuration file loaded are displayed at the top left-hand side of the screen. There are a number of green boxes on the status bar. These indicate peripheral systems under the supervisory control of the COMPEND software. In this case, there are 2 peripheral components. The slim box refers to the Serial Link Interface module, which provides a microcontroller-based distributed control and data acquisition interface between the front-end software and the machine. A green box indicates that two-way communications has been established between the PC and the interface. At startup, or when a different configuration file is loaded, the slim box will temporarily turn blue while the software configuration is downloading from the PC to the microcontroller. It will revert to green once the software has been successfully downloaded. The box marked drive indicates communication between the PC and the motor servo drive, which is under direct digital control. The digital boxes on the screen are all color-coded to indicate function. Red boxes indicate outputs to the machine, including switches and set points, and with a few exceptions will have up and down toggle switches. Green boxes are inputs from machine sensors. Blue boxes are calculated channels derived from a number of sensor inputs. If a peripheral device box on the status bar turns from green to white, this indicates a loss of two-way software communications between the front end and the device. If the box turns red, this indicates a hardware fault with the comms port or the associated interconnecting cables. All peripheral device boxes must be green for satisfactory operation of the machine. Once the software has loaded and the machine guard is fitted, pressing the blue reset switch on the instrument panel enables the emergency stop. With the air supply to the machine on, pressing the red load override switch in to release it activates the loading system. The switch is illuminated and the load actuator box on the screen changes from disabled to enabled. We can now run the machine under manual control. To apply a load, use the up and down arrows on the side of the red load set point box to adjust the load to the required value. Alternatively, you can double click on the set point box and insert a value using the keyboard. The resulting load, as measured by the loading system force transducer, will be displayed in the adjacent green load box. Now we can manually control the load. We can return to the machine to make a couple of adjustments to the setup. You will need to make these adjustments every time you fit a different test adapter. Different test assemblies have different masses, which have to be lifted by the loading system before a test load can be applied to the specimens. This means that the load reading will require zeroing to cancel the effect of these different masses on the load measurement. Set a small load set point using the up arrow on the load control box. Increase in small steps until the crossbeam just lifts off the column clamps, but the specimens do not come into contact. This will be the zero load condition for the specimens. Slowly adjust the zero potentiometer until the load on the screen display reads 0. Apply a load of about 50 newtons and wait until the specimens are in contact. The load reading on the screen will begin to increase. Then loosen the clamping screws on the rear of the friction force transducer and adjust the height so that the anvil lines up with the torque reaction block. Retighten the clamping screws. It may be necessary to adjust the anvil to ensure that it is in contact with the torque arm before the anti-rotation pins between the crossbeam and the adapter engage. Having made these adjustments, we can now revert to the PC and continue with this introduction to the COMPEND software. The test adapter torque arm is restrained by the friction force transducer, and the resulting torque is displayed in the green torque box. The friction generated by the test specimens is derived by dividing the measured torque by the specimen mean friction radius, which is entered manually in the friction radius box. If an incorrect value is used, the derived friction value will be wrong. Such an error, if identified, can be rectified during post-processing of the spreadsheet data. The value in the blue friction coefficient box is that derived from dividing the time-smoothed friction force signal by the measured load. The fixed specimen heater can now be enabled by clicking the up arrow on the red heater box. The temperature set point can now be set in just the same way as the load set point, using either the up and down arrows or by double clicking on the box and entering a value with the keyboard. The temperature, as sensed by the thermocouple in the side of the specimen bath, will be displayed in the green specimen temperature box. Note that large step changes in temperature set point are likely to cause the bath temperature to overshoot the set point. So under manual control, use small set point increments when adjusting the temperature. This issue is avoided with automatically controlled tests, where it is recommended that ramped set point changes are used. The motor can now be enabled by clicking the up arrow on the red motor box. The speed set point box can now be used to set the speed in just the same way as the other set points. The measured speed is displayed in the green speed box and the number of cycles in the green total cycles box. The count can be reset to 0 by pressing the up arrow on the red revolutions box. This is a momentary action switch, and the display will revert to count after a few seconds. A switch on the back of the instrument cabinet is toggled to either axial loading when using the machine with the axial loading bellows, or to radial loading when using the pin on V-block adapter. The green load configuration box indicates the position of the switch. This is to use to check if the switch is in the correct position depending on which adapter and configuration file are used on the machine. The final box to note on this screen is the green contact potential box, which displays a time-smoothed output from a Lum-Fury electrical contact resistance measurement circuit. Further details of this measurement technique and interpretation of the results are given in the manual. To record data while running under manual control, click on Data File on the toolbar and select Open Immediate Data File from the drop-down menu. This will open the COMPEND Immediate Data File directory. Either choose the name of an existing file to be overwritten or appended, or name a new file, then click Open. A drop-down menu will appear from which to select a data rate. 3 new boxes will appear on the status bar. The first of these will display the number of lines of data recorded. The third box shows the selected data rate. Click on the green Start box to start recording data. The box changes to a red box marked Stop. The data lines box value now increases as each line of data is added. To change the data rate while recording, click on the data rate box and select a new rate from the menu. To pause recording data, press Stop. To restart recording, press Start. To stop recording and close the data file, press Stop, then click on Data File on the toolbar and select Close Immediate Data File from the drop-down menu. To view the data file, from the same menu, select View Data File in Excel. Select the chosen file and click Open. The data file will now be displayed in Excel. The data is time-stamped and the order of the data columns follows the order of the boxes displayed on the screen page 6, reading top to bottom and from left to right. All boxes marked with the green square in the bottom left-hand corner will appear in the data file. To open an auto-scaling real-time graph, select Graph on the toolbar and create graph from the menu. The channels currently displayed are shown in the panel on the right-hand side. To edit the channel selection and change scales, click on Edit followed by Edit Graph Connections. This opens a new panel. To change the scale of a channel, select the channel from the list and edit the minimum and maximum values as required. Click OK to accept the change. In this example, we have changed the lobe range from 0 to 100 to 0 to 500. To remove a channel, return to the graph panel, select the channel to be removed, click Disconnect, followed by OK. To restart the graph, select Graph on the toolbar and Restart Graph from the menu. To add a new channel, return to the graph panel, select an unused graph connection in the left-hand window. The right-hand window lists all available channels. Select the channel you want and click Connect. Next, set a minimum and maximum value and click OK. The new channel is now added to the list of channels displayed and the trace appears on the graph. The graph is auto-scaling, so the trace is progressively compressed, with the 0 on the time axis the time when the graph was last started. This allows the operator to view the entire test from that time to the current moment. To close the graph, click on File on the graph toolbar and select Close Graph. Clicking on Test Sequence on the toolbar presents a menu allowing the user either to create a new 10 or 20-step test sequence file, or alternatively to open an existing test sequence file. Selecting an existing file and clicking Open generates 2 new windows. The upper window is Control, which is used to start and stop the test, and also to create a data file. The lower window is Test Sequence, which is used to view and edit the test sequence file. This window can be maximized either by clicking on the Maximize button or by double-clicking on the title bar. The control panel can now be minimized by using the Minimize button. Selecting File on the toolbar and Save from the drop-down menu will save the file. Selecting Save As will allow the file to be saved under a new name. The file name is shown at the top of the spreadsheet. Selecting View on the toolbar, followed by Reveal Comment column from the menu, will add a column for adding notes about the test. The next column is Step Number, which is the logical order of steps, but not necessarily the sequence in which they are executed. This column is followed by the Next Step, which defines the step-to-step sequence, hence the actual sequence of steps in the test. This column includes the facility to include loops and calls to subroutines. Right-clicking on the Next Step box will open the parameter window for the current step. In this case, if I click on the Next Step box for step number 1, the parameter window shows Go to Step 2, which is the next logical step and is entered automatically when the Next Step button is clicked. I can, however, manually enter a different Go to step, should I wish, thus creating a jump. The parameter box also includes facilities for program variable conditions, for executing a step, and for setting a loop count, which appears in the next column. We will cover this later in the presentation. The fourth column is step time in seconds. This can also be used to pause the test, for example, so that the operator can perform a manual task as part of the sequence, or to program conditional steps or jumps. Once again, this will be covered in detail later. Clicking on the step time box opens a parameter window. In this case, the selected step time is 2 seconds. The data mode column shows the data rate programmed for a given step. Clicking on the box opens a parameter box. The maximum data rate for low-speed data is once every 0.1 seconds, in other words, 10 Hz sampling rate. There is also the facility to program opening of a new data file during a test. Data files cannot be viewed when they are being written to. So if you're running a very long test and want to view blocks of data while the test is still running, opening a new data file and closing the previous file will allow the latter to be opened and viewed. The next columns all refer to control parameters corresponding to all the red box items on the main page 1 screen, including switches and set points. In this example, a test to ASTM D2266, the first step is used to set up some starting parameters before set point control devices are enabled. The temperature set point has been set to 20°C so that when the heaters are enabled, there is not a large difference between the set point and the ambient temperature. It's also sensible to do such things as including a reset of the cycle counter. Finally, it's sensible to set the speed set point to 0 rather than a positive value, so that motion does not start instantly as soon as the motor is enabled. In step 2, a load of 392 newtons is applied. You will see that the value 0R appears in many set point columns. This stands for zero relative. For example, the temperature set point for step 2 is given as 20C. Right-clicking on the value will open a parameter box in which the value can be set to 0R. This means that there is no change relative to the set point in the previous step. So in this case, the temperature set point will remain at 20C. The set point parameter box allows the user to switch between a relative value and an absolute value. As well as programming a fixed time, the step time can also be programmed as a conditional step using the associated parameter box. There are a number of conditions that can be selected. Right-click on the step time box. Select either of these options and a browse list of available parameters is presented. In this case, I have chosen step when greater than or equal to and load as the parameter, and entered a trigger value in the yellow box. The step time box now shows C step positive, indicating that a rising value conditional step has been programmed. The test will now move to the next step once the load has risen to 392 newtons. At step 3, the heater is enabled and a temperature set point of 75C is programmed with a ramp time of 1200 seconds, thus ramping the temperature set point from 20C to 75C at a rate of 2.5 C per minute. The transition to the next step is another conditional step and has been set when the temperature is greater than or equal to 75C. At step 4, the motor is enabled and the motor speed set point has been set to 1200 RPM with a ramp time of 10 seconds. The test will run for the required amount of time, in this case 3600 seconds. Don't forget to have a data mode set if you want to record any data. In this case, the data rate is set to collect data every 10 seconds. At step 5, the motor is stopped, and at step 6, the test load is removed. Finally, step 7 includes the exit statement as the next step. This defines the end of the program and closes the test. If you wish to run a test unsupervised, it is sensible to set alarms in the test sequence file. Click on Alarms on the toolbar. This allows the user to program high and low level warning and shutdown alarms on all analog, pulse counting and derived channels on a step-by-step basis. It is important to note that when a new test is created, no alarms are set. When creating a new test, it is important to set alarms suitable for the test parameters, or as an absolute minimum, use the Set All Steps to Default option to ensure that the test parameters do not exceed the machine's capabilities. Alarms may be set for each step in the test and for each required parameter, although it is usually only necessary to set alarms on the most important parameters, for example, load, temperature and friction. Use the up and down arrows next to the step number box to pick each step. Then set the alarm levels for the required channel from the list on the right. The alarm levels may be copied from one step to another using the copy step and paste buttons. When an alarm is triggered, a message will appear above the control panel and the event will be recorded in the data file. A shutdown alarm will terminate the test. If you have modified the test sequence file, save the changes, then click the Minimize button to revert to the COMPEND screen. To restore the control panel, click on the COMPEND icon on the bottom toolbar and select the item from the menu. If windows have been resized and moved on screen, the default layout can be restored by clicking Arrange on the toolbar. To run a test, start by clicking Data File on the control panel. Then select Open Data File from the menu. The COMPEND data file directory will open. Either select an existing file to be overwritten or appended, or create a new data file by entering a new name, then click Open. The data file name appears in the control panel box. Having checked that the machine is ready to run, press Start. If you have not previously saved your test sequence file, a prompt will appear. Next, a panel will appear to allow the operator to enter details of the test to be performed. This information will appear at the top of the data file. Once this has been completed, the test will start. When the test has ended, as with the manual test, click on Data File on the toolbar and select View Data File in Excel from the menu. The test sequence file allows loops to be programmed. When used in conjunction with a relative set point, loops allow the user to program incremental steps. In this example, I'm programming a loop to increase the load set point from the current 100 newtons in 100 newton increments up to 500 newtons. To do this, I start by inserting a new step in the sequence. Select the step which is to follow the new step. Click on Edit on the toolbar and select Insert New Step. The necessary notes can be added in the comment column and all the subsequent control parameters set, including setting the load set point to 100 newtons relative. A value 100R now appears in the load set point box for the next step. We have to make sure that all the other set points are correctly entered for this new step. Finally, we have to set the appropriate next step value and loop count. In this example, our new step is step 5. So to create the loop, we must set step 4 as the next step. If we now enter a loop count of 4, the test sequence will execute step 4 at the 100 Newton load set in step 3, then increase the load by 100 newtons relative to the previous value in step 4. Hence, the first loop increases the step 4 load to 200 newtons, the second loop to 300 newtons, the third to 400 newtons, and the fourth and final loop to 500 newtons. On completion of the required number of loops, step 5 will move on to the next logical step, which in this case is step 6. With the load increasing each time the loop is executed, it is important to set the alarms for the steps within the loop to values appropriate for the maximum set point value achieved during the loops. If we now run the test, we can observe what happens on the real-time graph. We will, of course, have to rescale the graph to accommodate the changed test parameters. You may want to run tests using a common test sequence, but with changes to a given control parameter. You could, of course, simply edit the test sequence file each time you wanted to change the parameter. Alternatively, the software allows the user to program a variable set point as opposed to a fixed value. The user is then prompted to enter the required value at the start of the test. To create variable set points, click on View on the Test Sequence File toolbar and select Variable Table from the menu. This generates a table for defining variable set points. In this example, I have defined test load, temperature, frequency, and duration as variable set points. Now click on the required set point box, for example, load at step 3. Instead of using a set point of 392 newtons, as shown, click on the Use Variable box and select Load from the list of previously defined variables. The value in the box now appears as a set point of V1. We can also use a variable for the value in a conditional step. So instead of using 75C, as shown here, we can choose variable V2 by selecting temperature from the list. Once we have defined all the required variables, we can save the test sequence file and run the test in the normal way. When Start is pressed, the previously defined variable table is displayed. The required values for this particular test are entered. When OK is pressed, the test starts as normal and runs with the set point values defined in the variable table. That concludes this instructional presentation. If you would like to access specific sections, please choose the appropriate place from the timeline.